For this exam one material, we're going to talk about the arteries, arterioles, the various vasculature structures, and how blood actually moves through these vessels. And this is where we're going to see that continuous theme, right? So that theme that I talked about last semester, where form follows function, right? So the way that the arteries look is going to be different from the way that the veins look, and that's because they have different functions in terms of the circulatory system. So before we get into the specifics of arteries, venules, veins, capillaries, etc., we're going to start with some physics. So we're going to look at the laws that govern how blood flows through vessels. And this is not only governing blood flow in our body through a vessel, but typically any liquid that's moving through any conduit. And when I say conduit, that can be a hose or a pipe, but anytime a liquid is moving through a conduit, the same laws that we're going to speak about today govern that flow. And so it also governs the way blood flows in our vessels, okay? All right, so we're going to speak about 3 factors that determine how blood flows. The first 2, and then tying them together, is a really important part of understanding this. So first of all, there's the pressure gradient, and the pressure gradient in the cardiovascular system, we've seen this before. We need a pressure gradient for blood to move, right? This is how we describe blood flowing through the chambers of the heart, from left atria to left ventricle. We had that high pressure in one chamber, followed by low pressure in another chamber. And so we had a gradient. That differential was a gradient that facilitated the movement of blood passively from one chamber to the next. So too does blood flow through our vessels in that very same way. There needs to be a gradient of high pressure to low pressure to facilitate that flow of blood. The second factor is resistance. Now, we cannot speak about movement or flow of blood without talking about any sort of impeding force. So any factor that's going to stop or impede blood flow through a vessel is going to be the resistance, and we must take that into account as we talk about flow. And then tying both of these together, specifically in the systemic circulation, is going to be important. We'll talk a little bit about the pulmonary circulation, but more importantly, what happens in the systemic circulation. Okay, what do we know? So we know that the circulatory system is closed. What do I mean by closed? What do I mean by a closed system? It's in a loop, right? So blood is never leaving the system unless there's some injury or tear to a vessel, and it's usually flowing in one direction, okay? So that's what we mean by a closed system. And so we can use this analogy of a water hose. So think about water in a hose as an analogy of how blood moves through our vessels. The heart would be the faucet, right? Think about that hose being attached to the proximal end, being the hose attached to a faucet. The water would be the blood, right, that's moving through the hose. And what would the hose be in an analogy? What would the hose be? Our vessels, right? The vessel would be the hose or the conduit that the blood is actually moving through. So if we think about that analogy, the force that is being exerted as blood leaves the heart is what creates the pressure to actually move that blood through our entire circulatory system, okay? Now, we know blood is going to flow from high pressure to low pressure, hence the gradient that we just talked about. There needs to be a high pressure area, and that's where the heart comes in, right? The heart is creating that forceful gust of blood, which is creating that pressure differential. We have a high pressure proximally and low pressure distally. That's giving us a gradient for flow, and more importantly, for unidirectional flow. This is why blood does not move backwards in your vessel. It has to move in one direction, okay? Now, we must take into account the resistance of that flow. Just like with our analogy, if we have a faucet and a hose and water, if I were to step on that hose, right, and the faucet is running, I'm creating some resistance. I'm creating some impedance or opposing the flow of that blood. And we cannot speak about flow without speaking about resistance. So resistance is what are the factors that may be interrupting or stopping that blood from flowing in that tube or in that conduit or in that vessel, okay? So having said all of this, we can deduce that delta P, and delta P just means the pressure gradient, i.e. the pressure differential, right, high to low. Delta P is the driving force that's actually pushing any liquid through a tube, and more important for our purposes, blood through our vessels, okay? All right. Now, the equation for flow would be delta P, which is our pressure differential, divided by R, which is the resistance. And I don't want you to memorize this equation too much, but understand the relationship here. The fact that flow, the movement of blood through our system, is related to the pressure gradient, right? If we have a high pressure gradient or a low pressure gradient, but we must take the resistance into account. So flow is equal to delta P, our pressure differential, divided by whatever resistance may be encountered. Any questions on that bit? Any questions so far? Any questions so far? Okay. So the big take-home message so far is flow, right? That movement of blood. And here we're using an analogy of water in a hose is related to the pressure gradient, right? We must have a driving force of a pressure gradient. And we have to take the resistance into account. Okay. Now, when we speak of flow, we want to distinguish bulk flow. So bulk flow is the flow, the net movement specifically, that is brought about by our pressure gradient. Okay, so we can have flow that's happening from one side to the other, but that net movement, that gust, that bulk flow is brought about by having a pressure gradient. And so the heart is what creates that pressure gradient, right? Think about it. If we didn't have the heart pumping blood through the circulatory system, the circulation would grind to a halt. It would just stop. Why would it grind to a halt if we didn't have the heart? What would we not have? A pressure gradient. We would not have a pressure gradient. That heart is creating the high pressure, right? Which is that one side of the gradient. And then on the venous side, we have low pressure. And so blood wants to naturally move from the arterial side into the left side or the venous side. And so the heart is what really sets the stage for circulation. And I really want you to remember that. Without the heart, blood would not flow through our vasculature because we would not have a pressure gradient. Let's look at the schematic diagram here on the right. So the first part of this image, let's move this. Okay, so the first part of this image, image A here, is showing two different containers. They're connected by a tube in the middle, and we have about 100 millimeters of mercury, and that's the hydrostatic pressure represented by the water in this side, and about 60 millimeters of mercury, which is the pressure on the opposite side, okay? And so we have a pressure gradient. Understand that first, right? So we have more pressure here than we do here, so the differential is 40 milligrams of mercury. Now, in order for blood to flow, we said that we needed this pressure gradient. So because there's a connecting tube, blood, or not blood, but liquid, but think in your mind the analogy of blood as well. Like this is the same way blood behaves. So the liquid will flow from this side on the left to the right side because of this existing pressure gradient, okay? Now, in image B, we lose the gradient. We have the same amount of liquid on both sides, i.e. the same amount of hydrostatic pressure, and so we don't have a pressure differential. Our delta P is now 0 milligrams of mercury, and so we have a flow of 0. This is a really important relationship to understand. If there is no pressure gradient, there is no flow, okay? Even if there's an open network of communication. Understand here, however, and I'll point this out, there may be water moving from one side to the other, right? Because water will move freely, it's an open conduit, but there will be no net accumulation on one side versus the other, and that's what we refer to as the bulk flow. So there may be some bit of trickling from one side to the other, but 0 bulk flow. Now in the third scenario, we have much more water on the left side, 200 millimeters of mercury, and much more water on the right side as well, about 160 millimeters of mercury. And so we have the same pressure differential that we had up here. So would we expect our flow to change? No, right? The flow will not change because the pressure differential is the exact same, or the pressure gradient is the exact same, okay? So this image is really just highlighting the directly proportional relationship between flow and that pressure gradient. If we have flow, we have a pressure gradient. If we lose flow, we lose the pressure gradient. If we increase the flow, if we increase the pressure gradient, we increase the flow. If we decrease the pressure gradient, we decrease the flow. Okay, that's a directly proportional relationship. Any questions so far? This is a lot of math, so I'm hoping I'm not losing you guys. Okay. All right. So pressure gradients exist across both our systemic and our pulmonary circuits. Okay, and we'll describe some of the differences shortly, but we want to understand how we determine the pressure in both of these systems. So we know that pressure in the systemic circulation is going to be, what is the pressure in the aorta, right? That's going to be on the arterial side, the far left side, versus what is the pressure in the vena cava, the far right side. And that's going to be our differential in the systemic circulation. In the pulmonary circulation, our differential is going to be different. It's going to be between the pulmonary artery. What chamber is the pulmonary artery leaving? What chamber is the pulmonary artery leaving? Right ventricle, right? So the pulmonary artery leaving the right side of the heart, deoxygenated blood, heading to the lungs, versus the pulmonary veins, which are entering what chamber? Left atrium, right? Left atrium. So we're going from the right side of the heart to the left side of the heart. And so the pressure differential in the pulmonary circulation is going to be much less, right? And we'll talk about that. But understanding where we find these different pressures is how we identify the pressure gradient from the artery to the vein of that specific circuit. Okay, I'll say that again. So in the systemic circuit between the aorta and the vena cava, that's where we have our pressure differential. For the pulmonary circuit between the pulmonary artery and the pulmonary vein, that's where we have our pulmonary, or our pressure gradient. And I'll illustrate this in a little bit. So if you're lost, just hang tight. Now let's look at how we actually measure those pressures, okay? So in the aorta, we talked about this value last semester, the mean arterial pressure. We described this as being the difference between the systolic and the diastolic pressure. And so in the arterial side, in the aorta, we can identify the pressure through this value, through the mean arterial pressure. Alternatively, on the right side of the heart, in the venous system, we identify the pressure as the central venous pressure, or the CVP, and these are the values that we compare to determine if there is a gradient, okay? So we look at the mean arterial pressure on the arterial side, we look at the central venous pressure on the venous side, and we can compare those values to determine if we have a high pressure to low pressure, basically if we have a pressure gradient. And so in order to calculate the pressure gradient, which is delta P, we simply subtract the central venous pressure from the mean arterial pressure, right? And think about it, the central venous pressure should be a much lower pressure. This is the venous side of the body. This is the right side of the heart. It's very far from the heart, which is like the pump of this circulatory system. And so by the time we get to the venules and the veins, pressure is much lower than they are in the arteries and the arterioles, okay? And so we subtract the lower pressure on the venous side from the higher pressure on the arterial side. All right, let's look at this graph. So this graph is gonna help us sort of make more sense of that. So here we're comparing the average pressure across several different vessels at the top here. So arteries, arterioles, capillaries, venules, and veins. And what we can see is that there is a drop off in the pressure, a significant drop off in the pressure as we leave the arteries and as we head towards the venules and veins. Although the pressure in the pulmonary circuit is much less, there still is a difference. So there still is a pressure gradient, okay? So we have a higher pressure in the systemic side, and that drops off significantly. And so too do we also have a higher pressure in the pulmonary side, which drops off significantly, and they actually meet at the very same place. So what this is pointing out to us is that there is a pressure gradient between the arteries and the veins, between the arterial side of the heart, the arterial side of the circulation, and the venous side of the circulation. And that is what keeps blood flowing, importantly, in a unidirectional fashion, right? From the left to the right.